In this video, we'll discuss the deformation of a uniform circular bar. Here, the circular bar is there. If it is solid circular bar is there, if it is subjected to the axial tensile load P, obviously it will undergo a certain deformation. It means there is a change in length. Okay, we need to find out how much is the change in length here. Okay, so here the figure is there. Whatever the if you will consider a circular bar, its length is L. Its length is L and diameter is D. Diameter is D. Okay. When once this circular bar is subjected to the axial tensile load P, it will undergo a change in length, and it means the length will be increases, the diameter will be decreases. So this dotted line, it will shows that the change in length and its diameter, it will be reduced. So after changing its length, the length of the changed bar is L plus delta L. Okay. So how much will be the deformation? How much will be the deformation of this circular bar when it is subjected to axial tensile load? That we need to derive here. Okay. So we'll start. Consider a uniform circular bar shown in figure. Okay. Now let L equal to length of the bar, D equal to diameter of bar, P equal to axial tensile load. Axial means it will be acting along with the axis of the bar. So that is called axial tensile load. Okay. Next, delta L equal to change in length or deformation. It is also called as deformation. How much deformation happens here? Okay. Now we know that the Young's modulus equal to E equal to stress by strain. This is the basic formula for Young's modulus. Stress by strain. That will be equal to, stress is denoted by sigma, strain is epsilon here. Stress divided by strain. So now we will calculate how much will be the stress in this after applying the load. What will be the stress? Stress equal to load by area. We know that load divided by area. This load is how much? Load applied is P. So area I am just giving as A. That is cross sectional area. Here I will write A equal to cross sectional area. Cross sectional area of the bar. Okay. This is stress. Now stress equal to load divided by area. That is Newton per mm square or something. Load is P applied here. A is cross sectional area. Now come to the strain. Strain equal to this is E. Strain equal to change in length divided by original length. That is strain, how much is the change in length with respect to original length. Okay, original length. So how much is the change in length? We can see here, that is del L. That is del L is the change in length. So what will be the original length? Original length of the bar is L. That is L. So this is strain. This is stress. Now you substitute stress and strain in Young's modulus. That is, this I will call it as equation A. Equation A. Therefore, equation A becomes, where is equation A? Equation A is Young's modulus E equal to stress divided by strain. Now substitute stress value and strain value. That is, E equal to, stress is how much? Stress is load divided by area. That is P divided by area. This is stress. Divided by strain is how much? Strain is change in length divided by original length. How much change in length with respect to original length? That is del L divided by L. So this will be equal to, how much we are getting here? That is P by A so P by A into L divided by del L. This is E. Now what we want? We want the deformation or change in length. How much is there? Okay. So we want the deformation. That will be equal to del L. Del L equal to PL by AE. Okay. This is the deformation of the bar. When it is subjected to the axial tensile load P, the deformation is PL divided by AE. This is the basic formula if you want to find out the deformation. So from this equation, what will come to know here? For the given circular bar having length is constant and its cross sectional area is constant, and for the applied load P, the deformation is inversely proportional to Young's modulus. So this is the final conclusion. For the given circular bar, for the area is constant, the length is constant, and for the applied load, that is also the constant load, the change in length, whatever the deformation is there, it is inversely proportional to Young's modulus. Okay. So for given length L and cross sectional area A, and the load P, deformation del L is inversely proportional to Young's modulus. That is, deformation is inversely proportional to Young's modulus. If P, L and A is constant. Okay. So this is how the relation between deformation and the Young's modulus. And this is basic formula for the deformation P L by AE. P, you know, applied load how much is there? Length already constant. A, it depends upon the different bar. For this bar, it is a constant circular bar. So A equal to pi d square by 4. Here A equal to pi d square by 4 because it is a circular solid bar. What is the d here? D is nothing but it is a diameter of the circular bar. Okay. So this is the deformation here. Okay.